All right, welcome back to our third part about how we can deform the Earth's surface and effects of plate tectonics that we can see in landform creations. We just finished volcanoes. We'll look at some folding and faulting and the results of the faulting with earthquakes as we move forward. So going back to plate tectonics, remember there were three types of plate boundaries. We had the divergent. Those created tensional stress where you're pulling apart the surface. We had the convergent where you had compressional stress where you're squishing the land together. And then the transform boundaries like the San Andreas Fault where you're moving past each other. So it's kind of twisting. It's creating what's called a shearing stress upon the rocks. And when we put stress upon the rocks at the Earth's surface, it creates different landforms and different features based on those stresses. So it's from plate tectonics. Remember, it's not those dragons pulling apart the Earth. It's plate tectonics. So if we look at compressional stress at what we would associate near a convergent boundary. Now the stress is spread out over hundreds of miles in both directions from the boundary. It doesn't exist only immediately at the boundary. It's spread out over a large area. One of the things that can happen to some of the rock is that we can cause it to fold. Just like if you had a piece of paper on your desk and pushing it in from both sides, it would fold in the middle as you got the two sides closer together. Now it's easiest to see, obviously, in sedimentary rock because what should have been flat layers now show the folds. We have different types of folds or names for the different types of folds. So the anticline that you see here on the far left, that's an upfold. And think of it like an A, where if you did a little cross line through here, it would look like an A. That's the upfold. That's the opposite of a downfold, which is the syncline here. So the syncline is a fold downward, and anticline is a fold upward. Notice that I'm focusing on the structure of the rock, not what it looks like on the surface. Because on the surface, because we see things erode differently, you may end up with a structure that is a syncline, but it is a ridge on the surface. And that's usually when you have something really erosionally resistant. This stops this from weathering quickly and everything else weathers away from it, so it leaves a ridge. Or you could actually have an anticlinal valley, and that's what you see here, where it's an anticline, but there's some weak rock here, so it erodes quickly. So even though it's an anticline, it still creates a valley. So I expect you to be able to recognize that the folding is a result of compressional stresses that we find near convergent boundaries. The anticline is the upfold, and the syncline is the downfold. Anticline upfold, syncline downfold. So here, anytime you see these types of folds, that tells you at some point this area was compressed. Just again showing anticlines and synclines over a much larger area. So just outside of St. George, Utah, it's on the road between St. George and Zion. Some of you may have driven this road. There's a large anticline. And this anticline is geologically important because it's really visible to see. I mean, even when you're driving through it, you can see on the left side, which would be the west, there's a line of rocks kind of tilted upwards. And then on the east side, the right side of the photograph on top, they're kind of tilted downward. So the bottom photograph kind of fills in that blank of what that anticline looks like. I remember as a kid, I think I could jump a Hot Wheel from one side of this to the other because you had a ramp on one side and a down ramp on the other side. The other reason it's famous that this is right at the edge of the Colorado Plateau before you get into the Basin and Range Province, which covers most of Nevada and parts of eastern California. And what created the Colorado Plateau is different than what created the Basin and Range Province. And so Colorado Plateau was compression, caused uplift, and this is an example of compression. And then later when we talk about the Basin and Range Province, you'll see that that area was stretched. So this is right at the edge of that. And you can see what happens. It's actually what's called a plunging anticline, which plunging anticlines won't be on the test. And it creates some unusual features on the surface, these V-shaped features, as those up-tilted rocks kind of dip downward into the ground. So that's the folding, and folding you find at convergent boundaries. Faulting happens with all three types of stress. So whether it's compression, tension, or shear, you can cause the rocks to break. They may not necessarily want to bend. They may be too well lithified. They may be too dense. The stress may happen so quickly. There's any number of things. But if the rocks break, they're going to move either away from each other, towards each other, or kind of in opposite directions on the Earth's surface. And those are the types of faults that are associated with different stresses. Just based on the arrows, you should be able to see that a normal fault is a tensional stress. You should be able to see from a reverse fault that you've got compressional stress. And then the strike-slip fault, this is that shearing stress. And each one of these three is associated with a plate boundary. I'm going to leave out thrust faults because they're kind of a special type of reverse fault, and we're not going to worry about those for right now. So the normal fault, when we talk about a tensional stress where we're pulling it apart, you're not going to get the Earth open up and create a giant chasm 1,000 feet deep of the rocks separating from each other. They're just too massive and too heavy. They're not going to want to pull away from each other and leave a gap. They're just going to slide away from each other. So as these move away from each other, by sliding down this slope, that's the fault plane, by sliding down this slope, it makes the two pieces a little bit farther apart. Now, if you were to look at this from above, you would see this green patch, but this would also be exposed. So that would tell you that these things have moved away from each other. So a normal fault, it's tensional stress where they're moving away from each other. And this is the part where it trips up students. I can do the technical definition, then I'll do the kind of vernacular definition and description. So normal fault, this fault line, you have a piece that kind of sits on top. Hopefully you can see that this piece, based on this line right here, is above this piece. Even though this piece is higher, that's not the question if we have to look at this fault plane. If you were going to lift these up vertically, straight from here, could you lift up this piece? No, because this wouldn't be in the way. So this is the piece on top. This is the piece on the bottom. So the piece on top is called the hanging wall. The piece underneath is the footwall. Going back a few years to my geology class with John Cooper at Cal State Fullerton, his way to remember it was, if you were to stand on this fault line underground, your feet would be standing on the footwall side. Well, you're underground and it's dark, so you're going to need a lantern. Where would you hang the lantern? So you'd hang it on the ceiling above you. So the hanging wall, if you're standing on it, is where you'd hang your lantern. The footwall is where you would stand. So in a normal fault, the hanging side moves downward relative to the footwall. So the piece on top moves down relative to the footwall. That's a normal fault. And if you just watch this thing over and over again, it becomes hypnotic, and then hopefully you'll see how the hanging wall moves downward relative to the footwall. And even here we can see that, all right, first we have to figure out what's the piece on top, which is the hanging wall, which is the footwall. We see this dark layer. There's no dark layer up here, but wait, there's a matching dark layer down here. So, and then this is on a slope. So this piece moved downward. Maybe this piece moved upward, but it's a relative direction. So this piece moved downward. So this is a normal fault where the hanging wall moved downward relative to the footwall. And here we have a series of normal faults. We'll talk about something like this on a larger scale when we talk about the Basin and Range Province, because that's stretching on a large scale. This is stretching on a smaller scale. I mean, this is a road, so these are only like tens of feet across. But you can see here's a normal fault. Here's a normal fault. Notice they're actually going different directions. But this nice dark line would have been up there, but it slid down. This dark line would have been up there, but it slid down. So those are two normal faults. And then this dark line would have been up there. It slid down. And so we've got a series of normal faults. Whoops. That's what happens when you accidentally hit your mouse when your mouse when you're lecturing. Now the reverse fault, this is associated with convergent boundaries. This is compressional stress. Well, we can't push the rock into each other and have them kind of squish and get smaller. So if I push them together, I'm going to end up breaking the rock and pushing one side up kind of on top of the other. So we still have our hanging wall and our footwall, but now the hanging wall moves up that slope of the fault line and the footwall moves down that fault line stress. And so the hanging wall moves up relative to the footwall at a reverse fault. So again, now we're going to look for how do we know what direction. So here's our fault line. So here's our hanging wall. Here's our footwall. What moved in what direction? We've got this nice layer of white here. Oh no, it's white over here. But this dark layer here lines up with this dark layer here. And actually this light color here lines up with this light color here. You can see that this one has moved up. And so the hanging wall moved up. That makes it a reverse fault. So this is evidence of compressional stress in Joshua Tree National Park. Now, a strike slip fault, this is where they're moving next to each other. You don't necessarily get vertical movement. We do a little bit with the San Andreas fault simply because it's not a nice straight line. There's a little bit of a curve to it, so we get a wee bit of compressional stress. So it's not a reverse fault from it. It's just kind of when we do get a strike slip fault, it's not uncommon for a little bit of vertical movement. But for our arguments right now, we're just worried about it moving next to each other in two different directions. So you'll notice it refers to right lateral and left lateral faults. If you're standing on this side of the fault line and you look across, what direction did the fault line move? It moved to the right. If I'm standing on this side of it and I look across, what direction did the fault line move? It moved to the left. You have to trust me that if you were looking in this direction, remember you're facing in this direction, that when you face from this side over here to this side here, it still moves to your right. And if you're standing over here and look across, it's moving to your left. So it's a right lateral or left lateral. What I'm getting at right now is that this San Andreas fault is a right lateral strike slip fault. The San Andreas fault is a right lateral strike slip fault. So the Pacific plate on one side is moving northward relative to the North American plate, which is moving southward. So any faults that are associated with the San Andreas fault, because remember these stresses are over a large area, we would expect them to be right lateral, and that's exactly what we find. So this is out in the desert, one of the 1990 earthquakes. We can see that it's right lateral as well. So we look across the fault line and we see that it's shifted to the right. It's what we'd expect from San Andreas type stress. Often people will hear about faults that they didn't know existed. Now obviously we know a fault goes through here because the road's broken. But what about over here? There's going to be some disruption of the surface, but give it just a couple dozen years and you won't be able to know that there's a fault line underneath the surface here. So it's not always this obvious when it moves. And again, here we can see that right lateral motion and the stress that's created over a large area from the San Andreas fault. I always thought this would be a cool house to have, where your house is on the North American plate, but your yard is on the Pacific plate. And you can see the stresses that it's creating. This particular area near Hollister, it's a little slow process. Some areas on the San Andreas fault will see sudden movements that are pretty drastic. The San Francisco earthquake saw about a 30-foot movement. This one we're seeing just a few millimeters a year, and those all add up over a period of time. Some examples that are some landforms that show the movement, that right lateral movement. This stream would have been coming from the hills and across the plain and eroding through here. Well, if this is the fault line and this is moving in that direction and the other side is moving in this direction, well, that stream is going to be moved over time. And so until it ends up following this path, and then this stream is now down here. This stream channel you see right here at one time was right here. I had to pause there briefly. My neighbors decided to be a good time to talk out in front of my office, which is the garage, by the way. And so I didn't want you guys to hear about pool supplies. So back to our faulting, and the San Andreas fault, it's a relatively large fault system. I mean, it extends the length of California. and then it goes offshore north of San Francisco. There's a similar fault of similar length that goes through Turkey. So they have similar conditions when we talk about earthquakes in northern Turkey. They're associated with their own long strike slip fault. Now, some of these faults create landscapes because of the faulting. As we stretch things apart, we're going to see the effects of it. And so a rift valley, now what kind of faults are these? So we've got the piece on top sliding down, the hanging wall is moving down relative to the footwall, we've got tensional stress. Right, these are normal faults. And so that block that drops down on a large scale can create valleys. Now the picture I showed earlier from Central America, that was on a small scale, only a few meters across. This is something that can be a few kilometers across. And these valleys are called rift valleys because it's as you stretch it, you create rifts. And so you get these downdrop blocks and the relatively uplifted blocks. And so of course, these were named by a German, so you're stuck with the German names of it. The Horst is the uplifted block, Horst high, and then the Graben is the downdropped block. And so when you see stretching, you might have just a single Graben and a single Horst, or you might have a series of them if the stretching takes place over a larger area. So the Red Sea, for example, that is a relatively large rift valley, but for the most part, it's a singular valley as opposed to a series of them. So when we see a series of them, that would be Horsts and Grabens, or as we call it in the Western United States, rather than using the German name, we call it basin and range. And so most of Nevada and parts of Eastern California and a little bit into Utah are these series of stretched area where you get a downdrop block from the stretching that took place. And if you've ever driven across Nevada in the middle, don't do it. It's a long way. It's a series of going up a hill, down across the valley, up a hill, down across the valley. So you're going up a horse, down into the Graben, and then up and over a horse again as you go through the Basin and Range province. Now, the Basin Range, we saw this before when we were talking about Santa Ana winds, because this is where that high pressure can develop over the Basin and Range province. But the high pressure has nothing to do with the Horst and Grabens. It's just that's where it developed. So this is Central Nevada, Horst and Grabens for days. All right, so when we come back, we'll talk about what happens when we see the movement on these different types of fault. And so the movement creates an earthquake. So part 4 will be earthquakes.